Starting this review, one thing that we need to go over and make sure that we understand is there's two types of stoichiometry problems that we can talk about. Okay, we have reaction stoichiometry and then we have element stoichiometry. Now, in element stoichiometry, we are basically dealing with just an element. And the conversion factors that we can have is we use the conversion factor of a mole. Okay, and a mole can equal 6.022 times 10 to the 23rd atoms or molecules. 1 mole can equal the molar mass, which can be found on the periodic table. The molar mass of an element is just the atomic mass. The molar mass of a compound would be the atomic masses all added together when we're looking at that. Okay, so when we're doing elemental stoichiometry, these are the conversion factors that we're going to be using. If the other type of stoichiometry is reaction stoichiometry, and the way that we know it different is that elemental stoichiometry is just dealing with an element like we see in question number 1. Reaction stoichiometry actually has a chemical equation in it. So when we're looking at it to tell the difference whether we use these conversion factors or when we add in our mole ratio and things like that, all depends on if there is an equation, a chemical equation or not. And there's not a chemical equation number 1. It says what is the mass of 28.1 moles of the element nickel. Okay, so when we're looking at this, it wants the mass of it. Okay, now remember that anytime we start with a mole, we will always end up multiplying. Anytime we start with anything else, whether it's molecules or a mass, we will always divide. So here we're starting with a mole. We're starting with 28.1 moles of the element nickel. Now, anytime we want the mass, anytime we see grams, we know that we are going to be dealing with this conversion factor. 1 mole equals the molar mass. And in this case, it's just the element nickel, so we know that it's going to be the atomic mass on the periodic table. So we know that 1 mole of nickel will equal its atomic mass on the periodic table, which we get that as 58.69 grams of nickel equals 1 mole. Well, since mole is on the top, we put the mole on the bottom. So we put 1 mole of nickel on the bottom, and we put 58.69 grams of nickel on the top. And we see that the unit moles cancel. And what we ended up doing is we ended up multiplying. We multiplied our moles times our grams, and we should get an answer right around 1649.19 grams of nickel for our answer. And all we did to get that is we just multiplied the top, and we essentially divided by 1 to get that answer. Okay, moving on to number 3, it says how many atoms are in 2.4 moles of zinc. Now, anytime it says atoms, we know that we are dealing with a conversion factor of 1 mole of anything, in this case it's zinc, will equal 6.02 times 10 to the 23rd atoms. And this is Avogadro's number, and this is our conversion factor we're going to use. Now remember, we always start with the number of the problem, so we're going to start with 2.4 moles, and we know that we're starting with moles, so essentially we're going to end up multiplying. And since moles is on the top, we put moles on the bottom from our conversion factor, 1 mole of zinc, and it equals the other half on the top, 6.022 times 10 to the 23rd atoms of zinc. And we go ahead and we multiply that out. Remember, when we're plugging scientific notation into the calculator, you want to use second comma. So what we should have is 2.4 times 6.022 second comma 23. And we go ahead and plug that in the calculator and see that we would get an answer of right around 1.44528, and it should say E24. And that is how many atoms of zinc we actually have. Okay, moving on to number 5, it says how many molecules are in 4.6 moles of helium. And it says molecules. Anytime it says atoms or molecules, we're always going to use the conversion factor of 1 mole of anything. In this case, it's helium equals our 6.022 times 10 to the 23rd, and that would be molecules of helium. Okay, and that's Avogadro's number. So we go ahead, remember we always start with the number in the problem, so we're going to start with 4.60 moles of helium. And since moles is on the top, we go ahead and look at our conversion factor, put that same unit on the bottom, 1 mole of helium, and we put the other half on top, 6.022 times 10 to the 23rd molecules of helium. We see their units cancel, and we go ahead and we multiply this out. Remember to use second comma, and we should get an answer right around 2.77 E to the 24th. Now in number 7 it says how many molecules are in 22.1 grams of, that is, nitrogen dioxide. This one's a little bit more complicated, so we're looking for molecules, so we know we're going to use a conversion factor. 1 mole of nitrogen dioxide equals 6.022 times 10 to the 23rd, and that would be molecules of nitrogen dioxide. But we see that we are starting in grams. Now anytime we have grams in the problem, we know that we need the molar mass. So we know that the 1 mole of NO2 is going to equal the molar mass of NO2, which we see that the molar mass is going to be nitrogen, which we have 1 of them, oxygen we have 2 of them, multiplied by their atomic masses. We have 16 for oxygen, nitrogen is 14.01. We go ahead and multiply those out, 14.01, 32.00, and we go ahead and we add those guys up, and we should get an answer right around, we'll just round it to 46 grams. Now what this means is 1 mole of nitrogen dioxide equals 46 grams of nitrogen dioxide. Okay, and we need this because we're starting in grams. Now remember, we always start with the number in the problem. So we're going to start with 22.1 grams of nitrogen dioxide. Okay, and we're going to use the conversion factors and look over here. And the only thing that has the unit that we're looking for grams of NO2, is right here. So we go ahead, we see it's grams of NO2, we're going to put that on the bottom. So we have 46 grams of NO2 equals 1 mole of NO2. Okay, so now that we use that conversion factor, it's gone, we can't use it anymore. So the next thing that we're looking for is moles of NO2. Well, our only conversion factor that has that now is going to be right here. Okay, so we go ahead and we put that on the bottom. We say that 1 mole of NO2, and put the other half on top, equals 6.022 times 10 to the 23rd molecules, and that's what we're looking for. So to plug this in the calculator, what we're going to end up doing is multiplying the top. So 22.1 times 1 times 6.022 second comma 23, enter, and then divided by our 46. Now when we go ahead and we do that, we plug that in the calculator, we should get an answer right around 2.89 E, which is times 10 to the 23rd, and that would be molecules. Main thing on this is make sure we have our conversion factors. We put that one because it said molecules. We put our molar mass because it had grams. Alright, moving on to number 9. It says how many atoms, so it wants atoms of sulfur are there in 2 grams of sulfur. Okay, so it said atoms, so we know that we need our 1 mole of sulfur equals 6.022 times 10 to the 23rd atoms of sulfur. And it said grams right here, so we know that we need the molar mass. So 1 mole of sulfur is going to equal our molar mass, which our molar mass for sulfur, since it's just the element, it's the atomic mass on the periodic table. So we go ahead and we look on the periodic table and we see that it's 32.07 grams of sulfur. Now we go ahead and remember we start with the number in the problem. So we go ahead and we start with our 2 grams of sulfur and set it up. And since grams is on the top, we look over here. This is the unit that says grams, so we put that on bottom. We put 32.07 grams of sulfur. Put the other half of the conversion factor on top, 1 mole of sulfur. And remember, once we use a conversion factor, it goes away. keep going. We have moles of sulfur on the top, so the only thing that says that is right there. So we put 1 mole of sulfur on the bottom, and 6.022 times 10 to the 23rd atoms of sulfur. We put that on top. Use that conversion factor. We got what we want, so we go ahead. 2 times 1 times 6.02 times 10 to the 23rd. Enter, all divided by 32.07. And we see that we would get an answer of right around 3.756, and that would be E to the 22nd, or times 10 to the 22nd atoms of sulfur. Moving on to number 11. Number 11 says the disinfectant hydrogen peroxide, which is H2O2, decomposes to form water and oxygen gas. And it says how much O2. So we're looking for how much O2, and it wants it in specifically moles. Okay, will result from the decomposition of 6.84 moles of hydrogen peroxide. So that's what we're starting with. Now, the difference between this problem and the problem that we've been working is that this gives us an equation. Okay, it's a decomposition reaction. It's starting with H2O2, and it decomposes into water, which is H2O, and oxygen gas, which oxygen gas is a diatomic, so it's O2. It's a part of Brinkelhoff. Now, in stoichiometry, especially reaction stoichiometry, you have to have a balanced chemical equation. So before we can do any math, we have to see if it's balanced. So all we're dealing with is hydrogen and oxygen on both sides. We see that on the reactant side, we have 2 hydrogens and 2 oxygens. On the product side, we see that we have 2 hydrogens and we have 1, 2, 3 oxygens. Okay. Now, whenever this happens, where we have an odd and even number here, what we like to do is there's 1 oxygen by itself, so we're going to go ahead and put a 2 right here. And what this does is it changes our oxygen to, now we have 2 plus 2 is 4, so it's an even number. It also changed our hydrogen to a 4, okay, because 2 times 2 gives us 4. So we have 4 hydrogen, 4 oxygen. To balance it over here, we just put a 2 in front of our hydrogen, and that distributes out, and now we have 4 hydrogens, and now we have 4 oxygens. And now it's a balanced chemical equation. Now, when we're dealing with reaction stoichiometry, after you have it balanced, you just want to deal with what you're dealing with. It says how much O2. So I go ahead and I box O2. And it says that we're starting with 6.84 moles of hydrogen peroxide. So we box hydrogen peroxide. And what we're doing by boxing this is we're giving us our conversion factor. The conversion factor that we always use in reaction stoichiometry is our mole ratio. And it comes from the coefficients in front. Okay, now oxygen doesn't have a coefficient, so it's understood to be 1. So what this means is that 2 moles of hydrogen peroxide equals 1 mole of O2. Now, since it doesn't say grams by oxygen or grams by hydrogen, this mole ratio is the only conversion factor that we need. If it had said grams by O2, we'd need the molar mass of O2. If it said grams by hydrogen peroxide, we'd need the molar mass of that. But since it wants moles of both, all we use is our mole ratio. So we always start with the number in the problem. We start with our 6.84 moles of H2O2. And we look in our conversion factor, and the only thing that says moles of H2O2 is right here. So we go ahead and we put that on the bottom. 2 moles of H2O2 equals 1 mole of O2. We go ahead and we work this out and be 6.84 times 1, all divided by 2, and we should get an answer of right around 3.42 moles of O2. Okay, now moving on to number 13. 13 is actually part 2 of 3. In the previous problem, what we did, what you should have done is we should have balanced the equation by putting a 2 coefficient in front of HCl. And in the previous equation, it tells us that this is what we are starting with. Okay, now in 13 it says what is the mass of magnesium chloride produced. Okay, so I'm looking for the mass of MgCl2. Okay, so I'm starting with just magnesium, and I want to figure out what's the mass of MgCl2. Okay, so in looking at this, we always box what we're dealing with and we write down our mole ratio. In this case, it's just a 1-to-1 ratio. So 1 mole of magnesium equals 1 mole of MgCl2, which is magnesium chloride. Okay, now the one thing here that's different than the problems we worked is it says what mass of MgCl2. Now anytime it says mass or grams, whatever it says by, we need the molar mass of that. So we need the molar mass of magnesium chloride, which we have magnesium and we have chlorine. We have 1 magnesium and 2 chlorines. We go ahead and multiply them by their atomic masses on the periodic table. We know that chlorine is 35.45, and we know that magnesium is 24.31. And we go ahead and take these guys, multiply them out, okay, and we get a molar mass of something right around 95.20. And what that means is that 1 mole of magnesium chloride equals 95.20 grams of magnesium chloride. Now the reason why we did this is because it said mass by magnesium chloride. If it says mass or grams, we have to find the molar mass. And then all we do is we start with the number in the problem that it gave us. It gave us 4.73 moles of magnesium. Okay, and we just look at our conversion factors. Okay, what's the only thing that says moles of magnesium? Well, that right there. So we put 1 mole of magnesium on the bottom, and we put the other half of the conversion factor on top. 1 mole of magnesium chloride. Okay, remember once we use it, it's gone. So we go ahead and we keep going because we haven't found the mass of magnesium chloride yet. And we see that moles of magnesium chloride is on top. Well, what's the only thing that says that? That right there. 1 mole of magnesium chloride equals, and we put the other half on top, 95.20 grams of magnesium chloride. Okay, we go ahead, we see that these units will end up canceling and we're left with what we want. We have the mass of magnesium chloride as our unit. So we go ahead and we multiply this out. 4.73 times 1 times 95.20. All divided by 1, and we should get an answer right around 450.296 grams of magnesium chloride. Okay, moving on to number 15. It says when sodium chloride reacts with silver nitrate, silver chloride precipitates. And it says what mass of silver chloride is produced from 122 grams of silver nitrate. Okay, when we're looking at this, the first thing we have to do is we have to write the equation. So we have sodium chloride. Anytime we write an ionic compound, we got to crisscross. And sodium's +1, chlorine's -1. We crisscross and we get NaCl. Plus, it gives us our silver nitrate, which silver is Ag. It has a +1 charge always. Nitrate's a polyatomic. It's NO3, -1. We crisscross and we get AgNO3. And what we should see by this is we're going to have a double replacement reaction, okay, because we have 2 compounds. So the sodium is going to replace the silver, silver is going to replace the sodium. So what we're going to end up with is silver chloride, and since everything has a 1 oxidation number, we know that it's just going to be AgCl. And the other compound that we're going to have is sodium is now bonded to nitrate. They both have a 1 oxidation number, so it's just NaNO3. And this is our chemical equation. Now the good thing about it, if we look at it, we see that everything is already balanced for us. So we can go ahead and we can start on stoichiometry. Now it says what mass of silver chloride. Okay, so it said mass of silver chloride, so anytime it says mass or grams, we know that we're going to need the molar mass of AgCl. Okay, so we're dealing with AgCl, and it says produced from 122 grams, so it said grams by silver nitrate. So we need the molar mass of both of these. Okay, but remember, the first thing that we always write down is we write down our mole ratio, which in this case it's 1 mole of silver nitrate equals 1 mole of AgCl. Okay, so it's a 1-to-1 ratio. So our next step, we have to find the molar masses. So in this one, we have 1 silver, 1 nitrogen, and 3 oxygens. So we go ahead and we add all of those up, and we should see that we get a molar mass of silver nitrate of right around 169.88 grams per mole. And when we add up everything for silver chloride, we have 1 silver, 1 chlorine added all together, and we should get a mass of right around 143.32. Now what that means is that 1 mole of AgCl equals 143.32 grams of AgCl, and 1 mole of AgNO3 equals 169.88 grams of AgNO3. Okay, so we go ahead, remember we have all our conversion factors written down. We go ahead and we start with what we have in the problem. We have 122 grams of AgNO3. Okay, so we look at our conversion factors and we go ahead and we see the only thing that says grams of AgNO3 would be right here, our grams of AgNO3. So we go ahead and we put that on the bottom, 169.88 grams of AgNO3 equals, and we put the other half on top, 1 mole of AgNO3. Okay, we cross that off the list because we used it, and we look up here and we see that we have moles of AgNO3 right here. The only other thing that says that is this conversion factor right here. So we have our 1 mole of AgNO3 equals 1 mole, we put the other half on top, so this half on top, 1 mole of AgCl, and we use it so it goes away, and we see we have 1 mole of AgCl. The only thing that says it is right there, so we put 1 mole of AgCl on the bottom, put the other half on top, 143.32 grams of AgCl, and we go ahead and we work this one out. And what we'll end up doing is we'll end up multiplying our 122 times 1 times 1 times 143.32 inner, all divided by our 169.88, and we should get an answer right around 102.93 grams of our silver chloride. Moving on to number 17, it says how much H2O is produced when 20,000 grams of C2H2 burns completely. And this is ethane burning completely. So on this one, main thing we have to focus on, it wants the answer in units of grams, so think of this much as grams. So first thing that we do is we look at our balanced chemical equation, and we're dealing with water and 20,000 grams of ethane right here. So we go ahead and we write our mole ratio. 2 moles of C2H2 equals 2 moles of water. Now the other thing we have to pay attention to is it says it wants how much grams in grams of H2O. So the next thing we need is the molar mass of H2O. We have 2 hydrogens and 1 oxygen, so 2 times hydrogen's atomic mass plus oxygen's atomic mass, and we get 1 mole of H2O equals the molar mass of it, which when we add those up is 18.02 grams of H2O. And we're starting with 20,000 grams of C2H2, so we need the molar mass of that. Molar mass of 2 carbons plus 2 hydrogens, so 2 times the atomic mass of carbon, 2 times the atomic mass of hydrogen, and we get the molar mass of C2H2 is going to be right around 26.04 grams of C2H2. Now remember, we always start with the number it gives us in the problem. So we start with 20,000 grams of C2H2. Now in looking at our conversion factors, the only thing that says grams of C2H2, which you have C2H2 there, my bad, is right here. So we go ahead and we put that on the bottom, 26.04 grams of C2H2. Put the other half on top, 1 mole of C2H2 and we keep going. Once we use it, we lose it. Okay, the only thing that says moles of C2H2 is this guy right here. So we put that on the bottom. 2 moles of C2H2 equals, and we put the other half on top, 2 moles of H2O. And that kind of goes away because we used it. It's gone. The only other thing, we look up here, it says moles of H2O. The only thing that says that is right there. 1 mole of H2O equals our 18.02 grams of H2O. So we go ahead and we multiply this out, 20,000 times 1 times 2 times 18.02, all divided by 26.04 times 2. If we're putting it in the calculator and you want to put it all in at once, make sure you put parentheses around this and parentheses around that. Plug it all in the calculator at once. Make sure you have your division sign right there. And the correct answer that we should get is 13,840.2 grams of H2O. Okay, moving on to number 19. Now number 19 is a little bit different than what we've been dealing with because it says we have 2.2 moles of zinc and we have 6.4 moles of HCl. And we see that these are both reactants. And it says react according to the equation. And it says if the limiting reactant is zinc, so it tells us that the limiting reactant is zinc, determine the amount of excess reactant that remains. Okay, so when we're doing this, what we have to realize is that when we have two numbers, okay, so it went from one number in the problem to now we have two numbers in the problem, we always use the limiting reactant. So if zinc is the limiting reactant, we know that our HCl is going to be our excess reactant. Okay, so it wants to know how much of that excess reactant do we have left over. So first we have to figure out how much we actually use. To do that, we're just going to do a mole to mole conversion between zinc and HCl, starting with our limiting reactant. Because remember, once we figure out what the limiting reactant is, we always start with that. So we're going to go ahead and do a mole to mole conversion. We need our mole ratio. 1 mole of zinc equals 2 moles of HCl. Okay, so we set it up. We always start with our limiting reactant. We're starting with our 2.2 moles of zinc. And since zinc is on the top, we put zinc on the bottom. 1 mole of zinc equals our 2 moles of HCl. And we go ahead and we multiply this out and we'll see we'll get 4.4 moles of HCl. Now what this means is this is the amount of limiting or excess reactant that we actually use. So we actually use 4.4 moles of HCl. What we actually have is 6.4. So to figure out how much we have left over, all we do is we go 6.4 moles of HCl minus our 4.4 that we actually used of HCl, and we get 2 moles. So what we will have left over of our excess reactant is 2 moles. Okay, moving on, we're going to actually do an even problem here just because we need to know how to do this. Number 20, it says, gives us the description of the reaction, and it says if 1.7 moles of CS2, which is carbon disulfide, is combined with our 1.33 moles of oxygen gas, identify the limiting reactant. So here, what we have to do is we have to find the limiting reactant. And what we want to do when we work with this is we just need to find out how much is produced. And the limiting reactant will always produce the least amount of what we're working with. Okay, so in this case, we go ahead and we take it. We take our 1.7 moles of CS2, and we can just pick any one of our products. Say we're going to pick our carbon dioxide, and we're going to see basically how much CO2 is produced. So when we're doing this, all we need is our mole ratio, and we have a 1 mole of CS2 equals 1 mole of CO2. Okay, so when we're doing this, we just have 1.07 moles of CS2. Set it up. Put 1 mole of CS2 on the bottom. We get it from right here. And 1 mole of CO2 on the top. We go ahead and work it out. We see that what we will produce is we will produce 1.07 moles of CS2. Okay? Now we're going to do the exact same thing for the other reactant. And remember, the limiting reactant will produce less. So here we have 3:1 ratio. So 3 moles of O2 equals 1 mole of CO2. Okay? So to do this, we go ahead, work the same thing out. We start with what the problem gives us. We have 1.33 moles of oxygen. Use our mole ratio right here. We have 3 moles of O2 equals 1 mole of CO2. And we go ahead and we work this out. And what we see will happen is we have our 1.33 times 1 all divided by 3, and we should get a mole of 0.44 moles, and sorry, this should be CO2, of CO2. And we see that oxygen produces less, and our limiting reactant will always produce less of our product. So when we're working number 20, our limiting reactant is going to be oxygen, because the limiting reactant always produces less. Okay, now moving on to number 23. Now, since we found out that oxygen is our limiting reactant, we know that we're going to start every single problem with oxygen. And it says how much SO2 is formed. So we have oxygen and we have SO2. Okay, so that's what we're dealing with, and we always start with our limiting reactant. So the first thing we do is we write down our mole ratio. We know that we have 3 moles of O2 equals 2 moles of SO2. Okay, so 3 moles of oxygen equals 2 moles of sulfur dioxide. Okay, and it wants to know how much is formed, and it just wants it in moles. So we're starting with moles, we're going to moles, so all we need is our mole ratio. So we start with the number of our limiting reactant, 1.33 moles of O2, and we start with that. Since moles is on top of O2, we put that on the bottom. 3 moles of O2 and 2 moles of SO2. Okay, and we go ahead and we work this out, and it'll be 1.33 times 2, all divided by 3, and we should get an answer right around 0.8867, and that would be moles of sulfur dioxide. Okay, moving on, we're going to do number 26, because number 26 is pretty hard. It tells us about the reaction. It says if 70 grams of CO, which we know that is a reactant, it says reacts to produce 65 grams of CH3OH, which that's methanol. What is the percent yield of CH3OH? So we know that percent yield is going to be our actual divided by our theoretical times 100. Now in this problem it says that it produces 65 grams of CH3OH. So we know that this is going to be our actual yield. Okay, so the only thing we have to do is we have to find our theoretical yield. Well, to find our theoretical yield, we're going to always do a gram to gram conversion between one of our reactants and our products. So what we have is, if we're doing a gram to gram conversion, the first thing that we need is we need our mole ratio, and looking at this we see that our mole ratio is going to be a 1-to-1 ratio. So we have 1 mole of carbon monoxide equals 1 mole of methanol. Okay. The next thing that we have to have in a gram to gram conversion is we have to have their molar masses. So in carbon monoxide we have 1 carbon, we have 1 oxygen. So we go ahead and we add those together and we get 1 mole of carbon monoxide is going to equal 28.01 grams of carbon monoxide. And we do the same thing for methanol. 1 mole of methanol, which is CH3OH, which in this case we have 1 carbon, 4 hydrogens, and 1 oxygen. And we go ahead and we add all those together and we get 32.05 grams of methanol. Okay, so we have all of our conversion factors that we need, so we go ahead and we start our problem with what it gave us. It gave us 70 grams of carbon monoxide, and since we have grams of carbon monoxide on top, we put grams of carbon monoxide on the bottom, which is 28.01 grams of carbon monoxide. It equals 1 mole, and once we use it, we lose it, and the only thing that says it is right here, so we put 1 mole of CO equals 1 mole of CH3OH. Okay, once we use it, it's gone, and then we see the only thing left that matches is right there, 1 mole of CH3OH equals 32.05 grams of CH3OH. And we go ahead and we work this out, and we see that we would get a theoretical yield of right around 80.0964 grams of our methanol. Okay, so now we have our theoretical. Here is our actual. So what we would have is we'd have 65 all divided by our theoretical of 80.0964 times 100, and we would get a percent yield of right around 81.1522%.